This conversation is powered by Google Illuminate. Check out illuminate.google.com for more.
Ever wonder what makes a good radio antenna? It's more than just sticking a wire up in the air, right?
Absolutely. It's the heart of your radio system. A bad antenna can really ruin even the best equipment.
So we're diving into antenna fundamentals today, a deep dive into the science behind those seemingly simple pieces of metal.
Think of it as the unsung hero of radio communication.
Exactly. Let's unravel the mystery, shall we? So let's start with antenna gain. It's not about making the transmitter more powerful, is it?
Nope, it's about focusing the signal. Think of it like a flashlight. A narrow beam is brighter than a wide one, even with the same bulb.
Right. So the isotropic antenna is our reference point, a theoretical, perfect sphere of radiation.
Exactly, it's our baseline. Real antennas concentrate power in certain directions, giving them gain over the isotropic ideal. We measure that in dBi. And dBd is relative to a dipole, right? A more practical reference. Then there's efficiency. Not all the power from the transmitter makes it into radio waves, right?
Right. Losses happen due to resistance in the antenna materials, the skin effect, and even dielectric losses in insulators.
And ground conditions play a big role too. Wet soil is better than dry sand for sure.
Absolutely. A poorly designed or installed antenna can waste a lot of power as heat.
Beam width is how wide that focus signal is, right?
Precisely. It's the angle where the signal strength drops off by a certain amount, usually 3 dB or 6 dB.
And for ground-based antennas, we have azimuth and elevation beam widths because of ground reflections.
Exactly. The ground can actually boost the signal, but it also affects the shape of the beam.
Bandwidth is the range of frequencies an antenna works well over, correct?
Yes. It's related to the SWR, the standing wave ratio. A good match between antenna and transmitter impedance is key.
So 2:1 SWR is usually acceptable, but lower is better.
Yeah, definitely. An antenna tuner can help, but it's not a substitute for a well-matched antenna.
Polarization is about the orientation of the electric field in the radio wave.
Vertical or horizontal, mostly. Matching polarization between transmitting and receiving antennas is crucial for good reception.
Except for ionosphere propagation, where it matters less.
I see, right. And circular polarization is useful for satellites that tumble in orbit.
Takeoff angle is important for long-distance HF communication.
A low takeoff angle means the signal travels farther before hitting the ionosphere.
More skips mean more signal loss.
Right, so lower is better for DX. Antenna height above ground is a key factor.
Matching feed point impedance to the transmitter is vital for maximum power transfer.
But even a perfect match doesn't guarantee good radiation efficiency. Radiation resistance versus loss resistance is key.
So a low SWR doesn't always mean a great antenna. Makes sense.
Precisely. It's about the whole picture, not just one number.
How does an antenna actually radiate radio waves? It's not just magic, right?
It's about the oscillating current creating an electromagnetic field that propagates outwards. Resonance is key for efficient radiation.
Your article mentions other antenna types like Yagis, dipoles, and more.
Yes, each has its own strengths and weaknesses depending on the application. There's a lot to explore.
So building a good antenna is a science and an art. It's about understanding all these factors working together.
It's about optimizing for your specific needs and location. Experimentation is key.
That was a great discussion. Thanks for sharing your expertise.